It's time for day 2 of the copper cycle, a preview of our year lab. So I'm going to open that up, switch to page 2, which is going to look like this, and look at the objectives, and we'll try and walk through the next couple of pages here. So we're going to start in this lab with elemental copper powder, perform a series of reactions, and finally recover that copper powder again. Along the way, we're going to make some new chemical compounds. So we'll be meeting copper hydroxide, copper oxide, copper chloride, and copper nitrate along the way. And so background information. So you'll want this for answering these questions down here. Copper can be found in the elemental form or as part of the compound. So copper might look like a nice ground up substance like this, or it might look like a penny. It might look like a copper wire as well. But when it's part of the compound, it might look different. So this is a copper compound. This is called copper sulfate, and copper is bonded to something called sulfate. So elemental copper means just the atom. So here we have a copper atom, as it theoretically might look. So when I look up copper on the periodic table, I see that there's 2 numbers. The atomic number is 29 and the atomic mass is 63.5. So if I round up 63.5 to 64, because on average they should be like that, we can figure out the number of protons and neutrons and electrons. So if you're going to draw it like you did in previous classes, you would write 29 p pluses, or 29 protons in the nucleus, 35 n zeros, or 35 neutrons in the nucleus. Now this would be really tiny, like you couldn't even see it if it were drawn at the scale. And then you'd start putting in electrons in the shell. Normally we say that the shells fill up 2, 8, 8, 18, up to 2 in the first shell, 1, 2, up to 8 in the second shell. And then after that, this model is a little sketchy, and we'll talk about different models of atoms later on, but let's stick with the 2, 8, 8, 18 model. And so the outer shell, which is called the valence shell, which is really important, valence, V-A-L-E-N-C-E, valence shell, that's the outer shell. In this case, ends up showing 2, 4, 6, 8, 9, 10, 11 electrons in the outer shell. So this is elemental copper, and again, that's copper that looks like a penny. Now, when copper bonds to something like with this stuff here, the copper sulfate, copper is said to be in a compound at that point. So this is copper to oxide that I'm showing you right here. So you draw a copper atom the same way as before, 29 protons, 35 neutrons in the nucleus, very tiny, and then you'd fill all the shells up like you did before. And what copper tends to do is it tends to lose 2 electrons to become happy or stable, but you still have 29 protons in the nucleus, 29 pluses, 27 minuses, 2 more pluses than minuses. So we say it has a 2 plus charge, or a 2 plus valence sometimes. And sometimes you write it as +2, and usually that's allowable to write either way. Oxygen, if you look at the periodic table, it has 2 numbers with it. It has an 8 and it has a 16. 8 is the number of protons, and then 8 plus some number of neutrons is 16. Well, 8 plus 8 is 16, so it has 8 neutrons. The number of protons initially dictates the number of electrons, so we would normally put 2 electrons in the first shell, and then we put 6 in the second shell. But oxygen often likes to have a full shell of 8, so it'll gain 2 electrons. 2 electrons have a negative charge, so we have 8 protons, 8 pluses, 10 minuses, 2 more minuses than pluses, so it gets a -2 charge. You might think of copper having a +2 charge and the oxide having a -2 charge, and opposites attract, so we'll make an ionic bond here. Look, they bond together. And so this would be a model of copper oxide compound. It's a compound because it's made of 2 or more atoms all stuck together. So you can use that information for answering these questions here. So this question and that question. What's an element? What's a compound? If you didn't catch it, go back and look at it again. Let's say that we have 3 atoms, atom A, atom B, and atom C. And we're going to make a compound out of them. So that means that they're going to bond together somehow or other. It could be a covalent bond, could be an ionic bond. And let's figure out the different ways that we can make this molecule. So we could have this one in the middle. We could have that one in the middle. Or I guess we could have this one in the middle. Now what happens if we take this compound, if I turned it around like this, would that be a different compound? The answer is no, it would not be a different compound. It's just, molecules and atoms and things are always moving around every which way. So this compound, compound is the same as this one, is the same as this one. So we can make different compounds by arranging those atoms. In this experiment, we're going to form several different compounds. We'll form copper nitrate, copper hydroxide, copper oxide, copper sulfate. So your job is to label and circle the nitrate, the hydroxide, the oxide, and the sulfate. So this first one is copper nitrate. Well, I can see copper is right there. So I'm going to label this, that's my copper. And then that must mean that this and this one right here are the other thing, the nitrates. N-I-T-R-A-T-E. N-I-T-R-A-T-E. So you might be wondering, how do I answer this question? So it says, please label and circle nitrate, hydroxide, oxide, and sulfate. So I would say you have about 3 options for answering this question. It says, label and circle the nitrate, hydroxide, oxide, sulfate. Write this. Cu is the copper, NO3 is the nitrate. And you could also draw it. So I just made a really bad drawing right here of this. So what I did was I went to insert, drawing, new, and there it was. Let's move on. Number 3, elements combine and or separate from one another during chemical reactions. If you watch this GIF or GIF, you'll see that we start off with N2 and H2 and it makes NH3. Let's refresh. So these are the reactants, the red together, the greens together, and now we have the products. 100% atom economy, all reactant atoms are present in the desired product. In a chemical reaction, matter can't be created or destroyed. So here it goes again. We start off with 2 nitrogen atoms bonded together, that's a compound. Started off with 3 hydrogen molecules, and we ended up with 2 ammonia molecules. Each ammonia, 2 of them, each one is made out of 1 nitrogen and 3 hydrogens. Next page. Chemists keep track of what's going on in a chemical reaction by using symbols and formulas. Tracking what happens depends on the fact that new substances are rearrangements of the original substances. For example, copper chloride is broken down to make copper atoms and chlorine molecules. This compound here is called copper 2 chloride or copper chloride. You can see it's bonded together right here. There's a bond, here there's a bond of some sort. So this is copper and chloride, so it's called copper chloride. And right here we have an arrow, that's usually called a yield sign. And so the reactants in this case are broken down to make copper atoms. Copper atoms, here's copper atoms, Cu, and Cl2, that's this. Why is it called Cl2? That 2 is a subscript in the bottom right hand corner. That means that these 2 are bonded together. It's not the same as saying 2 Cls. If we said 2 Cls, that would mean that these 2 are not bonded together. All right, so circle the reactants and put a box around the products. All right, so these are so you're going to put a circle right here because these are the reactants, and make sure you figure out what the products are. We've all heard that matter cannot be created or destroyed in a chemical reaction. Explain this statement in the context of the reaction above. Count them. We have 1 copper and 2 chlorides. Isn't that what we see right here? 1 copper, 1, 2 chlorides. Created or destroyed. It can help you do things in a safe manner. And I hope that by the time you're done with this class, you'll have internalized safety procedures and you'll be able to run your own labs in a safe and efficient manner. So what I'd like you to do now is to read everything starting right here all the way through the rest of the lab, and then I've made some questions here, and so all you have to do is look at these questions and think about them a little bit and then read through the rest of the lab and answer them, and that will be the end of this lesson.